Okay, here we go. Moving on to Unit 3, the periodic table. This is the first video in the series, video 3.1. Alright, continuing on with the periodic table unit, video 3.3. We need to talk about why the periodic table is called the periodic table. We talked about this a little bit in video 1, why the periodic table is periodic, and it's because as we go across a period, there are patterns that repeat itself. I want you to take a moment and write these notes down in your interactive notebook, and then we're going to talk about them. Alright, as you go across a period, the nuclear charge increases, which means the number of protons in the nucleus increases. Every time we add a proton to the nucleus, the positive charge of the nucleus gets stronger and stronger. And that positive charge of the nucleus starts to pull the electron clouds, the rings of electrons, more closely to it. So the rings actually get pulled in towards the nucleus. Alright, I drew a very rudimentary atom here on the screen for us to see. And I put an N in the middle for nucleus. We can also say that it stands for neutrons. But I'm going to draw the protons in. So let's say I take a proton and I put it in the nucleus. Okay, that little black dot, which was supposed to be blue. Okay, that blue dot right there, that's a proton. When that proton pulls on these electron rings that are out here, it pulls them in towards it. As I keep adding more protons into the nucleus, the rings get pulled more closely to the nucleus. So the radius of the atom starts getting smaller. Every time you add a proton to the nucleus of an atom, the radius gets smaller. That's what we're saying. Whoops, how'd that get back there? That's what we're saying right here. It's pulling the electron cloud in more tightly towards the nucleus. What is not happening is we are not adding enough electrons there to shield the nucleus. So there's something called electron shielding. When we have a nucleus, I'll use this atom down here because it's already drawn for us. When we have a nucleus right here and we don't add more rings, these inside rings, the first 2 electrons here and these 8 electrons here, are preventing the nuclear charge from attracting this outside ring. We call this shielding. These electron rings are shielding these outermost electrons. So the more electrons you have on the inside, the more they are shielding the electrons in the very outermost ring. Because when we are adding a proton across a period, we are not adding any more rings, we are not increasing the shielding that those electrons are feeling on the outside ring. You can see here that it says shielding does not increase. And the reason that shielding is not increasing is because the kernel electrons, the electrons that are on the inside, not the valence electrons, the inside electrons are interfering with the attraction between the protons, the neutrons, and the valence electrons. So these are the shielding electrons. Every element in the same period or row, that means the same row across, has the same number of kernel electrons, 2-8. We did not add any more rings to shield those electrons. So what happens is, as I increase my nuclear charge, that nuclear charge gets strong enough to start pulling that outermost electron valence shell in closer and closer to the nucleus. So as I go across a period, my radius of my atom is going to get smaller. And we can see that here in this diagram. Look at period 2. Let's get a pointer. I'm a pointer? Okay. Period 2, if we look here at lithium and beryllium and boron and carbon, see how the the atom is getting smaller and smaller as you go across? The reason for that is because you're adding protons to the nucleus, and that nuclear charge is pulling those electron shells in closer and closer to the nucleus. Now, as you go down the group, we'll look at group 1 here. Group 1 is hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. As you go down the group, why do you think the atom is getting bigger? Well, what are we doing as we go down the group? We are adding a ring of electrons. So as we add the ring of electrons, the shell they get bigger, and they make the atom's radius bigger. Alright, we have to talk about something called ionic radius. Ionic radius is the radius of the atom compared to the ion. When you have an atom that is gaining electrons, the radius of that atom is going to get bigger. And the reason for that is because the electrons are repelling each other, and they are going to be a little bit further away from each other. So as you gain electrons, your radius increases. Please write that down in your notebook. Non-metals gain electrons, their radius gets bigger. Remember, the non-metals are on the right side of your periodic table. You did not change their nuclear charge, you didn't change the number of protons, but you have more electrons because you gained electrons. And because they are negative, the electrons are repelling each other, and they're outnumbering the protons, and they're going to drift further apart from the nucleus. They're going to try to get as far away from each other as possible. Metals, on the other hand, tend to lose electrons. When they lose electrons, the radius is going to decrease. When you lose an electron, there's less that the protons have to pull on, and so they are able to pull those electrons in a little bit closer to the nucleus. And because of that, the radius of the atom decreases. Alright, new vocabulary word. That vocabulary word is isoelectronic. And isoelectronic means they have the same number of total electrons as something else. So let's say we're looking at sodium. I'll just write sodium here. A sodium atom, so it has no charge. The electron configuration of a sodium is 2-8-1. When the sodium the sodium atom loses an electron, so it loses this electron. Let's get black here. It becomes the same as the electron configuration of 2-8 because it lost that electron. That electron went to visit Grandma over there somewhere. Hello, electron, I love you. Okay, wait a minute. That's Grandma's house. A bad house. Let's draw Grandma. Hey, you gotta entertain yourself somehow. Okay, so it loses that electron. That electron goes away and visits Grandma. Now, sodium has an electron configuration of 2-8. But sodium is not an atom anymore. Sodium became a positive charge. So sodium with a positive charge, +1 charge, has an electron configuration of 2-8. It's still sodium. You didn't change the number of protons. You only changed the number of electrons. So sodium +1 is isoelectronic with a noble gas. Look here at the periodic table that I just pulled up, and you'll see that neon has the electron configuration of 2-8. So sodium +1 ion, the sodium +1 ion, is isoelectronic with the neon, because the sodium lost an electron and became 2-8 instead of 2-8-1. Alright, go and get yourself your chemistry reference tables. I want you to look at table S. On table S, there are two vocabulary words that we have to address, and the first one is electronegativity. I grabbed my table S, and I'm going to zoom into the electronegativity. You can't see. Oh, there we go. So now you can see the element's name, and you can see the electronegativity. Electronegativity is how strong an atom is. It's a number that is based on an arbitrary scale from 0 to 4, where we take 0 and we make it the weakest element there is, and we take 4 and we make it the strongest element it is. So when we have an element with an electronegativity of, like, say, 0.6 or 0.7, it's relatively weak. So if you were to walk up to that element and you were to get a fight with that element, then you would be able to probably win, because the other element has a good chance of being a little bit stronger than the element with an electronegativity of 0.6. So these are like our ratings of how strong they are. And what I mean by getting in a fight, well, they're fighting over electrons. Remember, we always want to get a full valence shell. So if you have a 0.6 as your electronegativity, and you walk up to hydrogen, which has a 2.2 as its electronegativity, and you get into a fight over electrons, hydrogen's going to win, and the guy with the 0.6 is going to lose. Metals tend to have very low electronegativities. Nonmetals tend to have very high electronegativities. So let's look at the notes here that you're going to be writing in your notebook. Electronegativity is its desire to gain electrons. The stronger you are, the more you're going to want to gain electrons. You're going to win those electrons. I always think of electronegativity as being how strong an atom is. Nonmetals have very high electronegativity. They're strong. They gain electrons to make their octet full. Remember, your octet is your 8 valence electrons. Metals tend to lose electrons to achieve full octet. They're like, oh, I'm weak. I'm not even fighting you. Take my electron away. They have very low electronegativities. You can look up your electronegativities on table S. So if they ask you what the electronegativity is, it's very easy. Just go on table S, look it up. The most electronegative element, the one that is the strongest, that is going to fight and take away your electrons, happens to be fluorine. Let's see if I can write that in there. There we go. And the least electronegative element is francium or cesium. Okay? So we've seen those guys before, where fluorine was the most reactive nonmetal and francium and cesium were the most reactive metals. That's not a coincidence. Alright, when we go across a period, we go from left to right across the period, electronegativity is going to increase. You're going to get stronger as you get a fuller and fuller octet. You don't need to memorize this. What you do need to do is you need to be able to look at your table S, and you need to be able to tell what is the electronegativity doing across a period. I suggest that you write down all the elements in the period, and then you just write the electronegativity underneath them, and you can see, does the electronegativity go up or down as you go across the period. Alright, the other vocabulary word that we have to talk about is ionization energy. Ionization energy is related to electronegativity, but it's not exactly the same. Ionization energy is the amount of energy needed that somebody else needs to take your electron away. So if we go back to an example where we're talking about money. If I want to take an electron away from you, and you are a very strong element, then you're going to need a lot of money to buy the electron from that very strong element. If you are weak, then the charge for your electron is going to be very low. You're going to need very little ionization energy to take the electron away from the weak element. Ionization energy is the amount of energy, or the amount of quote-unquote money, that somebody needs in order for them to take the electron away from you. So it is related to electronegativity, but it's not the same. Alright? As you go across a period, ionization energy does get higher, because if you get more strong as you go across a period, you're going to need more money to buy the electrons from that particular atom. Again, ionization energy is also listed on table S. Make sure that you know where to find ionization energy. And if you look at this little diagram that we have here, you can see the ionization energy goes up till you get to neon, which happens to be a noble gas. Neon, you need the most money because neon has a full octet. the octet is complete, and Neon's like, I'm not giving up my electron. I'm gonna charge you an arm and a leg in order to get that electron away from me. So Neon, Argon, Krypton, and Xenon have the most or the highest ionization energies because it takes a lot of money, a lot of energy to get an electron away from them. Alright, so we got another little diagram here. Going down a group, ionization is going to decrease. Why do you think it's going to get cheaper and cheaper to buy an electron from an element as you go down a group? The reason is because those electrons are getting further and further away from the nucleus. And you've got these electron rings that are not valence shells. They're kernel electron rings that are inside, and they are shielding the protons from those outermost electrons. Remember, those protons in the nucleus are trying to hold on to those electrons. So if I put stuff in between them, they're shielding them. They're shielding the protons so the proton can't hold on as tightly, and it gets easier and easier to remove an electron as you go down a group. Think of it this way. If you have a $100 bill and you're holding it very close to your heart, so imagine you're hugging this $100 bill, it's going to be very hard for somebody to take that electron or that money away from you. If you have an electron or a $100 bill and you've got it held between your thumb and your pointer finger and you're holding it way out at arm's length and some bad guy comes by, it's very easy for them to grab that $100 bill from your fingers and take off down the street. So the further away your electron is from your nucleus, the easier it is for somebody to come and steal it away. Ionization energy decreases as you go down a group because those electrons are getting further and further away from the protons, which are holding onto those electrons. Alright, we're almost done. The electronegativity the reactivity of elements has a trend as well. And let's talk about that really quickly. As you go down a group on the metal side of the periodic table, so let's look at the metals on the left side of the periodic table, over here. Pointer, where are you? Here are my metals, okay? As you go down a group, you get more and more reactive. Remember, it's all related. So if you can take an electron away from francium very easily, that is its reactivity. Lithium, the electron is closer to the nucleus, closer to the protons, so it's holding on tighter to that electron. Francium, however, has its electron, this one itty-bitty electron. Come here, you. This one itty-bitty electron right there there's a 2, an 8, an 18, a 32, an 18, an 8, and then this 1. See how far away it is from the nucleus? The 2 and the 8 are not written there. If you look at the bottom of your periodic table, it tells you 2-8 is not written. And the reason it's not written is because they ran out of room in the box, okay? So it says dash 18. So here, 2-8, 18, 18, 8, 1. That little 1 right there is 1, 2, 3, 4, 5 rings between the 1 and the protons, which are over here. So it's because there's 5 rings there, somebody can easily snatch that 1 electron away, making it a very reactive atom. Same thing with francium. Now let's take a field trip. Let's zoom in, okay, to the other side. Fluorine is the most reactive nonmetal. Let's examine why. So we've got the protons, which, let's pretend that these are the protons right here. That's the nucleus. And here are the rings, right? 2-7. Remember, those protons are holding on to the 2 and the 7 electrons. Fluorine wants to go out and find an electron. Well, that proton's pretty strong. Those protons are really strong and very close to that ring of electrons there. So as soon as it gets close enough to another atom that it says, oh, I got an electron, that proton is strong enough to pull those electrons, that electron from somebody else, and use it for its own valence shell to complete its octet. So fluorine is reactive, but for a different reason. It's reactive because it can steal electrons away very easily. The protons are very close to that shell of that valence shell right here, and it's going to go out and it's going to steal electrons from anybody it can get its little fluorine hands on. Okay, let's see. Let me zoom back out. Hold on a second. Let's make sure we covered everything. Here, we've got reactivity, ability, or tendency of an element to go through a chemical change. Which ones are going to be the most reactive? Bottom left, we got francium, most active metal, fluorine, most active nonmetal, and we just discussed the reason why. Rewind me if you need to hear that again. Metals are losers. They tend to lose their electrons very easily. Nonmetals are the ones that are the bullies. They tend to gain their electrons from other atoms. Can't compare metals and nonmetals, okay? The reason you can't really compare them is because they do it for different reasons. The metals lose their electrons more easily because they get further and further away, and fluorine gains the electrons because it gets closer and closer. Going across a period, reactivity decreases. You get less and less reactive, okay? The reason why you get less reactive as you go across a period is because your nuclear charge, your number of protons, increases, and your shielding does not increase. You don't add more rings of electrons as you go across. Going down a group, the reactivity is going to increase because you're going to lose your electrons when your electrons are way out at arm's length. They're not close to the nucleus. Alright, I hope that helped with trends of the periodic table. You should know the vocabulary electronegativity. You should know ionization energy. You should know reactivity. You should also know atomic radius. Okay? If you have trouble with any of these things, please let me know. Until next time.